let's copy and paste. So mostly this is about the casting. The casting process, we pour the molten metal into the mold, and there could be different types of molds: insulating mold, like sand mold, and conducting mold. So we have to find out the time for solidification. So let me show you what I'm explaining. I'm alluding it to you some a little bit earlier. So we already covered mechanics review, thermodynamics, and heat transfer. Now we are going to cover fluids review. So these are the engineers who helped us understanding the fluids, review laminar flow, energy of the fluid, Bernoullis equation, energy of the fluid through the channel. When we pour anything into the channel, so the energy remains constant. The sum of energies, potential energy, pressure energy, kinetic energy, all these energies, the summation is constant at any cross section of the pipe. Suppose we are having the fluid passing water flowing into our pipelines like copper pipes or copper tubing or other PEX piping. So we have kinetic energy. So the summation. So we will learn about the equation of Bernoulli's equation, and we will find out some interesting features in that. So let's talk about the Reynolds number. This is the Reynolds number, and rho times velocity times the diameter. The diameter of the pipe, the viscosity. Viscosity is the resistance to flow. If the viscosity is very high, resistance to flow is high, like honey versus gasoline in a pipeline. So you see, so honey resists, the flow of honey is slower as compared to the gasoline or water because the viscosity is higher. So in the denominator, viscosity, with the unit of viscosity is Pascal second. So we'll study with this. So critical Reynolds number. Reynolds number, if it is less than or comparable to 2000, is very laminar to very laminar flow, and is going to start transiting from laminar to turbulent. And is begin to form if the is high, is higher than 2000. But you will have a threshold. So these are the thresholds of, if you find the laminar flow, it should be 2000 or less than 2000. We will do the problems later down the road, how to find out the flow type using this formula. So please write down this formula in your formula sheet. So, and then we will apply. If the fluid is flowing and very, very high Reynolds number like 2000, 20,000 is like a very turbulent flow. So 2000 and 20,000 are the thresholds for identifying the flow is turbulent, flow is laminar. Okay, let's do one problem here now. So let's see this problem. Okay, open your calculators. Okay, please collect the data. Read the problem and collect the data and apply the Reynolds number formula. Okay, so you will help your professor. So let me show you. I will help you. You will help me. We will solve the problem. Okay, Reynolds number. Reynolds number. How fast would a stream of honey, 1 inch diameter? So this pipeline is about 1 inch in diameter. Okay, the diameter is 1 inch and need to be turbulent. So Reynolds number is rho times velocity times the diameter divided by the viscosity eta. Viscosity is given 189 poise and the density is 1.43 grams per centimeter cube. Can you try applying this number and let me know? $20,000. For turbulence, starting the turbulent is a very turbulent. So he asked me the good question. Very turbulent is 20,000, but I will say start with a 2,000. Let's apply the starting point when the eddies begin to form. Sorry about that. I gave you 20,000, but can you plug in 2,000? So first of all, I would say let's do one thing one by one. So density, can you convert density from grams per centimeter cubed to kilogram per meter cubed? Let's make the units consistent to MKS. SI system like meters, kilogram, second. What do you suggest me? What is the rho in kilogram per meter cube? Yeah, one student says 14.3. And the unit of viscosity should be Pascal second. Pascal second is like 10 poise equals to 1 Pascal second. So let me convert with the density from here 1.43. So we know 1000 grams equals to 1 kilogram, and we know that 100 centimeter is in 1 meter. But here these are cube. So I'm gonna do the cube here. So this cube is cancelled by this cube. So you're left with the. Can you do the math here? One. Let me do the math and help you. What I'm getting here. So 1.43 times 100 power 3 divided by. I get 1430. So let's write it down. 1430 kilogram per meter cube. And let's do the convert the viscosity into Pascal second. Okay. Now we know the viscosity is 189 poise at 20 Celsius. So at higher temperature, the viscosity goes down. Okay, it makes sense. So the temperature is also important criteria for finding the viscosity here. So let me write down viscosity equals to 189 poise and 10 poise. So I can write down 10 poise equals to 1 Pascal second. So you will cancel poise with poise. 18.9. The answer is 18.9 Pascal second. You understood the conversion, right? And now we will go apply in the Reynolds number. Reynolds number formula is this one. So the question was asked, what value of Reynolds number should we use when it starts becoming turbulent? It is begin to form. So use this number. 20,000 when it is very turbulent. So let's use the 2000 number. Reynolds number equals to rho times velocity times the diameter divided by the eta viscosity. 2000 equals to rho is 1430. Velocity, we want to find out the velocity, and the diameter is in inches. Can you convert it in meters? How many meters in 1 inch? 0.0254 divided by the uh, eta viscosity 18.9. Can you find out velocity from this relationship? What do you guys get? 1040. Agreed. So this is a very high velocity. So at this velocity, the honey will starts making turbulences when it is flowing. Okay, let's do one more, although it's not here. Can you plug in 20,000? Let's see. What is the velocity of honey in the same pipeline when you have 20,000 Reynolds number? Just for intuition purpose, okay? Can you open your calculators and help your professor? What do you guys get? It should be very high, in my opinion. 10 times the first one. You see, it's very high, very turbulent. Have you guys understood? Now let's go to the next concept. Let me copy and paste this solution from the slides. And next week you might see similar problems. I'm gonna open another homework for practice, the casting and the fluids review. And before the quiz is Tuesday. Please write down the next equation, Bernoullis equation. Pressure, P atmospheric, zero is usually atmospheric pressure, okay? And rho v square over 2 is the kinetic energy, specific kinetic energy, and rho gh, potential energy, and P atmospheric at the second stage. You have to mark the points. For example, let me show you a casting, okay? Suppose this, just a very rough sketch, okay? Just this is a sprue and this is a casting, and you will see some castings they have open risers, some castings they have blind risers. Risers are also when you pour metal, the gate, this is known as the gate of the entry gate. Like we go to the subdivision, we have the entry gate. So it's an entry gate when the metal goes inside the casting. And then uh, you have a parting line here. the lower portion and the upper portion, and then you see the sand casting. And now you, after these are the risers. You know why do we provide risers? Because the solidification process shrinks the casting, and then that shrinkage losses are filled by the riser molten metal, because it starts solidifying here as well, so it cannot compensate that shrinkage losses. So those risers, they are very helpful, blind risers, open risers, to cover the shrinkage losses. You see my point? So now it's just, so then you will mark 0 point is atmospheric pressure, like over here, zero atmospheric, because it is open to the casting, like in our room. You are, we did some experiment long time ago, but right now I'm not able to do produce the same process here experiment, but just imagine. So this is point one, this is point G. Point one and G, they have the same level of potential energy. But point one, rho G H1, you see the height. We will solve such problems. I'm just taking you to that stage from here, that how are you going to apply this Bernoullis equation to find out the potential pressure at that uh, this is the pressure, potential energy, and sorry, rho gh is the potential energy, and the pressure P1 is at this stage, density, gravity, height, losses due to friction. Have you noted it down? Another equation which is very useful for our Bernoulli, for our continuity. Yeah, I will provide you these slides. You don't have to take the pictures. I will provide you all the handouts, and please write down this equation of continuity. Okay. A is the area cross section of the sprue or the pipeline, and V is the velocity of the fluid passing at that stage. Okay, I mark the stages here, like stage number 0 and stage number 1, stage number 0, stage number, or the state number gate. You see my point? So velocity. Continuity means the fluid is same, flowing with the same volumetric flow, meter cube per second. If you take the area is meter square, velocity is what? Meter per second. So it is known as meter cube per second. Volumetric flow, we also call it as a volumetric flow. Agreed? So now there is another form. We also call it as a Q. Q is the discharge or volumetric flow. Q is also known as the discharge rate. Uh, or we also, like if you open the faucet, then the fluid starts flowing through the faucet. Everybody washes hands, washes face in the morning, and then we use Q. We also call it as a volume per unit time. There is another formula. So I'm giving you some formulation, like volume over time, area times velocity. These are the same things. You see my point? Volume meter cube per unit time. And you can also convert this into kilograms per second with the density. Let me double check it. I will tell you later, but let's write it down. Okay, let's do one problem. Please draw the sketch of this casting, sand casting mold. This is sand mold. You are pouring iron, liquid iron, into a mold. The mold has a sprue. We call this as like a triangular shape as the sprue where the molten metal goes inside. Okay, the sprue liquid iron, it goes into the mold. This is known as the whole process is the mold. The mold has a sprue height of 2 inches. The height of the sprue from here, from this, the height is how much? Height is 2 inches. Okay, so high, so if I consider this as 0 point, this as 0.1, so you will mark it, Professor, h1 is equal to 2 inches, and this is known as the datum line. This is known as the, so the datum line above the height is how much? 2 inches. Agreed. And now the bottom of the sprue has a diameter. So bottom of the sprue has the diameter d1. D1 equals to a 0.2 inches. And now the next point, it says, next point, let me cut and paste the next slide here. What should be the diameter of the gate, the entry to the mold, the casting? What is the diameter? Um, you wish to pour the metal so that you do not entrain. You will not entrain. Air should not enter. Okay. So I would say Reynolds number for this case should be 2000. Okay, you understood that point. And what is Reynolds number? Rho V over. Okay, now let's try to understand. This is point one. This is point G. So if I zoom in, this is point one. This is point G. Okay, let me show you how I'm gonna start the problem. I'm gonna start the problem with a Bernoullis equation. Let me copy some um, further parameters like density, and we need to know the values below 20,000 are okay in casting, but let's keep it 2,000 for particularly laminar flow. Bernoullis equation, continuity equations. So we already know what is Bernoullis equation and continuity equation. Some of the data you can copy here. Iron has a density 7,860, and viscosity at the pouring temperature is centipoise. Which is equal to 2.25 in 10 to the power negative 3 Pascal second. 1 Pascal equals to 1 Newton per meter square. So in 1 Newton meter per square. So area 1 is given pi r square in meters. Please note it down. Ignore the friction losses. So let me write down the Bernoullis equation. Pressure at 0 point, kinetic energy at 0 point, potential energy at 0 point equals to pressure at the bottom of the sprue kinetic energy at the bottom of the sprue, and potential energy at the bottom of the. This is the friction losses, which is zero. Ignoring the friction losses, can you find out V1 from here? Because we need that V1 in continuity equation, which is A1 V1 equals to AG VG. Because as I mentioned, this is a sprue, and the sprue has the bottom, and then it has a gate, and this gate, you have to compare the states at the gate and the bottom of the sprue, and then this equation will help me to find out the velocity, and we will apply it in our Reynolds number to find out the velocity. So we have to find out the diameter of the gate, which can be found from the Reynolds number. Okay, so I'm going to take you over there. At the end, we will apply. Once we know the velocity at the bottom of the sprue, we will compare with the continuity equation, and then we will use this equation at the gate, rho v g. Let me rewrite here clearly. Then I will take you over there, but let's do this v1. So let's see, what is the pressure? P0 is atmospheric, agreed, and P1, it is also open to the atmosphere. You see, when the sand is in, like in our room, so its pressure is same even at 1, at G, at pressure is everywhere atmospheric pressure. So can I write down P1 as atmospheric pressure? So can I cancel this part from this part, right? Can I, because they are both atmospheric pressure. Agreed? Now you will tell me what is the velocity uh, of the fluid, molten state at zero. When it starts pouring, you assume this negligible is small, like zero velocity. So can I write down V at zero of the fluid of molten iron is zero? Can I write down zero? Because it is just to start, like you are just to pour it through the some bucket, you pour it inside the sprue. So I will mark it as, so this is zero. And how about the height? So the datum line is selected as the position where it is zero. So the height over here is 2 inches. So I can write down rho gh. Rho gh. Let me write down rho gh0. And rho is 7,860. Gravity is 9.8, and the height is how high from the datum line? This is my datum line. Agreed? How high that the top of the sprue? This is 2 inches, which is equal to 0.051 meters. Agreed? So can I plug in over here 0.025? Let me write down again 0.051. Please open your calculators. And what do you get? 0.051. How much is the answer for that? 39.8 uh, joules per kilogram. Now, this is the pressure, the potential energy. Now, we have finished the left hand side of the equation. Agreed? Let's go to the right hand side. Right hand side, V1 we want to find out. Agreed? We want to find out V1 square. How about this potential energy at the datum line? What do you suggest me? Zero, right? Yes. Yeah, kilogram, joules per kilogram. 928. I did not check it. Let me ask anybody else. Can you please verify? One student says 3928. Any other body who can confirm? You confirm it? 3928. He confirms it. You confirm it. She confirms it. Okay, let's do the right. Make sure that the quantities are same. So let's complete. I'm going to focus on this part. Look, how about this one? 0. So let me write down the equation now. I'm going to write down the equation here, and rho g, sorry, rho g h0 equals to rho 1 v1 square over 2. Can I write down like this? Rho is actually, it should not be 1. It should be same. Okay, agreed? So rho is cancelled by this rho and h0. So v1. What do you guys get for v1? Is it 1 meter per second? Can you make sure that the answer you get at the bottom of the sprue is 1 meter per second? He confirms it. You confirm it? You confirm it? Everybody confirm. That's good. Let's do the. I can write down again rho g h divided by. So it's 0.05. You confirm it? Yes. One student. Any other student who confirms v1 is 1 meter per second? He confirms it. You confirm it? Okay, that's good. Good job, guys. So let me write down now. Look, can you find out Reynolds number at this velocity? Rho v rho v1. So 7860 times 1 times the diameter. What is the diameter of the bottom? The diameter of the bottom, look, is 0.2 inches. Can you convert it into meters? Point 0.00508 divided by the eta. So the viscosity, let me double check. The viscosity is 2.25 centipoise equals to 2.25 in 10 to the power negative 3 Pascal second. So 2.25, because we know that 10 poise equals to 1 Pascal second. And 1 poise has 10 centipoise. So you can convert from 2.25 centipoise, 10 centipoise equal to 1 poise, and 10 poise equals to 1 Pascal second. So poise cancels, centipoise cancels. So 2.25 divided by 70. Sorry. I'm sorry. This should be 100. Do you understand the mistake? So this is correct now. 2.25 into 10 to the power negative 3 Pascal second. So you plug in this value, 2.25 into 10 to the power negative 3. And let me know, what do you guys get for the Reynolds number? If you do the math, is it less than 20,000? If it is less than 20,000 in casting, it is still okay. I think this is 17,746, which is less than 20,000. Although the more perfect answer is about 2,000, but even if it is less than 20,000 casting, it is still okay for having no eddies. You understand that? Everybody is with me. Now let's find out the gate. The question is find out the diameter of the gate entry. Okay, can I use the equation of continuity, this equation, to find out the gate diameter? So I'm going to use this one to find out the gate diameter. So let me tell you, the gate diameter is pi r square, like a cross section. Okay, pi r square. And now you can write down, let's write down AG VG equals to A1. What is the area at the bottom of the sprue? This is 2.03 in 10 to the negative 5. 2.03, 2.03 in 10 to the power negative 5. Agreed. And the velocity at the gate is 1 meter per second. Agreed. So now you find out AGVG, which is equal to this value. So which is equal to 2.03 in 10 to the power negative 3. Can you negative 5? Can you plug it in this equation? Reynolds number rho VG dg divided by eta and make it as 20,000. 20,000 is still okay in casting. And can you solve for this value? Vg dg combined. That will give you another equation, so you can plug it in over there. So what do you guys get? So let me write down 20,000 into eta is how much? 2.25 in 10 to the power negative 3. Agreed? 2.25 in 10 to the power negative 3 divided by 7,860. And that is equal to how much? Let me calculate it in my calculator. 20,000 2.25 negative 3 divided by 7860. I get 0.0057. So can I write down like this in scientific notation? Vg, this product is helpful to find out. So 5.725 into 10 to the power negative 3 meter cube per second. Meter meters square per second. And we have another equation. Look, we have another equation, this one. Now you will write down, this is equation number 1, this is equation number 2. Can you compare these two equations? But this equation has area. You know area equals to pi r square or pi d square over 4. It's just, so can you plug in? Let me write down this equation in the form of the diameter. Let me write down this equation. This is just a rearrangement manipulation, and this one area is pi d square over 4 into times velocity at the gate. That is equal to the right hand side. You see, the that is equal to how much? So if you do the math here, can you plug it in? That is equal to 5.2.03 in 10 to the power negative 5. Can I write down like this? Area pi by 4 times dg. What is dgvg? This is over here. So can I write down 2.03 in 10 to the power negative 5? And let's plug it in over here. 5.72 in 10 to the power negative 3. And let's find out dg from here. And here you get the answer. This is about diameter of the gate is 4.5 in 10 to the power negative 3 meters. Please confirm. It is not unreasonable because the diameter of the bottom of the sprue, how much is the diameter? That the bottom of the sprue is 0.2 inches, which is about 0.05. Do you understand this question? Will you be able to solve such problems in your quiz or test? I'm going to provide you with the Bernoullis equation, continuity equation, Reynolds number. These three equations you should practice. Any question, ladies and gentlemen? So let me repeat some of the questions. We need to find out the velocity. First step we have to do is find out the speed of the molten metal at the bottom of the sprue through the Bernoullis equation. So this is the Bernoullis equation, okay? And we can assume that if there are no friction losses given in the question, you can assume there are zero friction losses. And pressure is atmospheric pressure on both states, positions. And then use the Bernoullis equation, which helps you to find out the velocity at the bottom of the sprue. And then the bottom of the, once we know, you can plug it in the Reynolds. And once you know the velocity, you find out using the Reynolds number and see whether the flow is less than 20,000. In casting, it is okay. And then continuity equation will help you to move from the bottom of the sprue to the gate of the mold. Agreed? So that way you can find out the area of the gate entry. And then you can use this equation, Reynolds equation. You will have two equations. From the continuity equation, you will have this answer, and you will have another equation, Reynolds equation. Two equations, two unknowns, you can solve the problem. You understand the step-by-step method? So any question, ladies and gentlemen? We have reviewed some basic fluids. Combination of three equations discussed can be used to determine the processing conditions. So let me show you some of the casting processes and the capabilities and find out the defects. Like adding, when the air is entrapped, it causes bubbles. When you open the casting, it has some bubbles. We have to avoid those bubbles. So these defects. So let me show you the casting processes. Are you able to see in your handouts? I provided you these slides. Can you open these slides? Yeah, on the D12, casting 0. The slide, she says yes, he says yes, she says yes. That's good. By the help of casting, you can manufacture very complex shapes because you don't have to machine it, okay? You don't have to machine the type of the parts made like big, uh, uh, usually aluminum blocks, engine blocks, where the piston they are move up and down. These blocks are cast, and the pipes, some cast iron pipes, and jewelry. So long time ago in a history, Egyptians era, so they used to cast their jewelry in difficult shapes when there was no lathe machine, no CNC machines at that time. Just they can melt the gold, and the gold can be poured into the difficult, beautiful shapes like roses, flowers, and the ladies they wear the jewelry, the fire hydrants. They are cast iron. Uh, they are cast. Okay. So, what is the quick route from raw material to finished product? You melt the metal, you pour and or force liquid into hollow cavity, which is known as the mold, and you let it cool, which is also known as solidification time. I will give you some formulae how to find out the time to solidify the casting in the later slides. And then you remove the casting and you do some finishing process like using the buffer or some little bit sanding to make it more shiny surface. Some of the slides you will study on your own when you go home, like theoretical, raw material, atmospheric pressure, heating, furnace. So you heat the raw material, it becomes molten using some inert gases or vacuum. Some types of furnaces, the blast furnace, basic oxygen furnace is used to mold the to melt the metal. Some other furnaces like electric arc furnace, oxygen lens furnace, how to melt the metal. Another type is induction furnace, electric furnace. So complex 3D shapes can be cast, near net shape, low scrap, relatively quick process, intricate shapes, large hollow shapes, no limit to size, reasonable to good surface finish. We will talk more about surface finish in machining process. When you're using lathe machine, surface finish R square, there is a formula. So I'm just taking you over there, but not now. First we finish casting, then we go forging, rolling, extrusion, drawing. Those deformation processes is the next step. Then comes the other sheet metal forming. How do you find the sheets of the car body? Okay, you do the sheet metal working. Then we after we do that, we will go to plastic or machining. Over there, we will learn about the CNC or lathe machine, how to do the turning, facing, and these processes are important. What is the cost of manufacturing? Because you burn the tool when you are moving a rough cut, fine cut, you burn the tool and you put some new diamond tips on the tool. We are going over there. One day you will learn that before the end of the semester. So all these machining processes, so you should be able to find out the important parameters such as the power required to turn the machine. Okay, now dimensions, you can go up to as small like 1 millimeter or so. Tolerances and surface finish, 1 to 3 microns or 10 to 25. In sand casting, you have a little bit rougher surface as compared to the die casting. Die casting is like a steel mold. You force the model metal inside the die, and you have less rough surface roughness, which is about 1 to 3. Very fine casting comes out of the die process. So these are the different types of processes. Okay, so they are available in the market, and these processes are named on the type of the processes, such as sand mold. You use sand, which is very cheaply available, and you break the sand mold and you move the casting out. Shell casting. Plus, I'm going to show you the types in the next slides. These are the different types which you can understand. As I mentioned, you will study the slides later by yourself. Sand casting, mostly 60% of the uh, casting is done in sand casting. 60%, quite a lot. Then comes 11% permanent mold casting, die casting next, because to make a die is expensive. Centrifugal casting, as you know, centrifugal forces, the like our dryer machine, the clothes they go to the circumference of the drum, and the molten metal, when the centrifugal forces the molten metal, they go adopt the shape of the centrifugal drum. Shell mold, you make a shell mold, and then so you make ingots. Ingots are like a small pieces of cast metal, and you use them to deform into the forging process. Okay, you need to have some kind of material for deformation process, such as rolling, extrusion, drawing, forging, and those ingots are made in the casting process. 85% ingots are made in the casting process. Those ingots are used to find further deformation process. Cast to near shape, about 15%. So ingots are also known as the iron or steel molds, and water cooled molds, continuous casting. In the permanent mold, we have die casting, hot chamber casting, cold chamber casting, expandable molds. Those molds, they need to be broken in order to take the casting outside them. So we have a sand mold, a shell mold, a slurry mold, investment lost wax or lost foam. Like you have a wax mold, and when you pour the metal, the wax melts out, and the remaining part goes into the mold. Shapes casting is in the centrifugal, like pipes, spinning. Sand casting, the 60%, let's understand the nomenclature of the 60%. Okay, so if I give you this small quiz question, can you label this casting? The flask, sand, parting line, gate, choke, runner, mold cavity, and sometimes we need to have a hollow mold. So we put some uh, piece of core or sand so that the metal will not go and cover that area. The cope is the top part, the drag is the bottom part of the sand mold. Open risers, as I mentioned, those risers are used to cover the shrinkage losses during the solidification process, so that there will be no hollow cavities inside the solid part. These are some vents for the air which goes outside the atmosphere while there is a shrinkage solidification process. The sprue is the like a triangular shape where the metals. You see, this comes out of the when you break the sand casting. So the actual casting is the gray color part. The remaining parts are all extra metals which are solidified. You have to cut them off, finish them in order to use that actual casting in the machine or somewhere else. The pouring basin is also there, and the sprue side riser. Risers are used to cover the shrinkage losses. Top risers, wherever you feel the deficiency, there is a formula which I will tell you that there is some requirement at a certain distance you need a riser. Like in our case, look over here. Let me show you. In this problem, how many risers? Three risers. At a certain distance, you need another riser, an opening in the sand mold, the cope. You provide an opening so that when you pour the metal also goes into the risers automatically. That molten metal comes back into the mold. You see, because their solidification time is a little bit lesser. Cope is the top part. You have two parts, okay? Top part and the bottom part. A large industry is using the sand mold when the molten metal is poured into the sand mold and generates the required shape. This is the process. You first make the mold and the pattern making, core making, gating system. It comes in the form of the molding. Once you make the mold from sand, then the melting of metal is used to pour into the mold, and then solidification happens, casting, you shake out, remover of riser and gates, heat treatment, cleaning and finishing, and inspection defects dimension. So these are all the processes of the sand casting method. It's not required to learn these slides. This is just for your own knowledge purpose. Um, if you want to further understand later down the road about casting process. So you see, these are the manufacture parts in the casting process. You see how difficult shapes are made in during the casting process. This is V6 engine, the block of the V6 engine, and then these are the rotors of the brake system, some heat exchanger system, some transmission gears, these transmission blocks. These are all cast. You see multiple cars, millions and millions of cars are on the roads. They are all using the sand casting process. You see that? So that's very important process. And then comes the permanent mold casting where we have a die. In the die process, we make the dies first of out of the metal, maybe steel or alloy steel, so that it is permanent. You don't have to break the die. You just open the die and knock out the part outside the die once it is solidified. And the gating system is the bottom. You pour the through the sprue, and the gates are at the bottom of the mold. There is a riser over there as well. Once it is solidified, then you open the there are two parts of the dies. One is the right and left, or top and bottom, and then you remove the part out of the die. Low pressure casting. Another type is low pressure casting, where the pressure automatically uh, pulls the metal, molten metal inside the die. Die casting with a high pressure. One was a low pressure, one is a high pressure. These are the types of the casting. The knockout ejector pins. Once you open the die and you knock the pins, knock out the part through the pins. The die casting machine. The whole machine is having a die casting machine. I would suggest when you go home, just read through these slides when you have some time. I'm not gonna ask you labeling these die casting. Okay, these are just for your knowledge purpose, how they are made in different types of casting. They are all casting types: squeeze casting, die casting part like camera. You see, the molten plastic is injected into the die. Difficult shapes of plastic is made inside the casting process. We call it as a die casting. You make a die in steel and you push the metal, sorry, molten plastic into the die. We will study. I'm gonna teach you the die casting of plastic as a separate class. We will have we will spend time where we learn plastic injection molding and plastic injection extrusion. Okay, we learn this in the later stage. Continuous casting. Why do we say continuous casting? Because it is not uh, just one a small billet. It is continuously metals keeps coming into the mold, and it shapes takes, and we do the cooling process while it is going through the mold and acquires the shapes, and we start cooling, and is continuously coming out of the like a small hanger wire. Continuous casting, you see, the molten metal takes the shape of a pipe when it is continuous casting, and you keep cutting the pipe using the torch. Then we make a shell mold. Shell mold is also expandable. So when you pour the metal inside uh, the backing material is there, you make a shell halves and it requires the shape of the shell. Investment casting, you make multiple parts in one casting using, that's why we call it an investment. You are not wasting time. Vacuum casting, because of pressure difference, the molten metal goes into the die. Investment casting versus the conventional casting. Surface finishes difference in investment. Lost form, like you have a styrofoam, the shape you when you pour the metal, the foam burns out, burns away, and you are left with a blank. You see these shapes, the styrofoam has its all defects into the, if you take a closer look, these small grains are because of the burning of the styrofoam when the molten metal comes in contact. Centrifugal, as I mentioned, like a dryer drum, the centrifugal forces pushes the metal towards the circumference of the material of the die, which is like a hollow cylinder. It requires this. The pipe casting process. The directional casting process. So it is in one direction, starts solidifying in one direction and keeps on going into the other direction. And the casting characteristics. The process is sand, um, the porosity, dimensional accuracy, surface finish to 5 to 25 microns. So you learn about the processes and capabilities in these slides. Do you understand the types of casting process? Yes. Okay. Let's do the next topic. This is as an engineer, I will focus more on the analysis and time, find out the time to solidify the molten metal. So after this, I will give you a break of 10 minutes so you can relax. Melting and pouring. Okay. You study already in casting the first slides. You study about the processes, different like sand casting, die casting, investment casting, all these processes you studied. Now we are doing the next topic is analysis, melting and pouring. And as I mentioned, the step-by-step method, the first step is to melt the metal. Second step is to pour or force the liquid metal into the hollow cavity. And third step is to let it cool or solidify. Fourth step is to remove. And the fifth step to make it finish, remove the riser, remove the sprue, only the casting part which we need for our purpose. Okay, you understand that? So please look at this. When you melt metal initial time, the sensible heat and latent heat. When the phase changes, it's a latent heat of uh, fusion. You understand that? And then pouring happens when it is a little bit higher than the uh, a little bit higher than the melting point, and then you start pouring it. The temperature is a little bit higher than the melting point, and when you pour it, and then solidification happens. During the solidification change of phase, temperature remains constant. We use the uh, latent heat. Okay, we already saw this slide earlier, that how do you melt a metal inside the furnace. Raw material known as charge, and the atmospheric pressure heating happens, and furnace material refracted. Heat to melt. Please write down this formula. How much heat required to melt a metal? Rho is the density, V is the volume. This is the, look, this is the sensible temperature. Whenever there is a change in temperature, then it's a sensible heat, like a either rising temperature, heat of fusion, rising. You see, upper. So this is T melt. You see my point? T melt. I'm sorry, this is T pour. This is pouring temperature. This is T melt. And this is initial temperature. You see all these, we will learn it. When you open this, I will teach you at that time. So how much time required to melt a metal is by this form. Estimate the time, energy divided by power. Um, so at this time, you're having a break now, okay?